This is the final presentation on the series dealing with transmission lines and characteristic impedance. Let's write down previous results. Our schematic, recall, was a model of our inductor, our resistor, our transmission line from X to X plus dx, a conductance leakage term, a capacitance term to ground for our transmission line. We had C dx as the parameter, 1 over G dx as our leakage current term. The voltage drop was minus R dx, and the inductance was minus L dx. From previous results, we know that Z0, our characteristic impedance, is equal to R plus I omega L divided by G plus I omega C square root. Now we take the approximation in which we have the resistance of the core of the transmission line going to 0, in other words, a very low resistance value, and the leakage current going to 0. In that case, Z0 equals to I omega L over I omega C square root. I's cancel, omega cancel, and we are left with this familiar expression, Z0, the characteristic impedance for a transmission line, is the inductance over the capacitance. So far we have not talked about the geometry of the transmission line. These have just been very generic terms. Now let's go ahead and consider a concentric circle geometry that of course is going to come to your mind as the coax cable. It's going to have an inner diameter D1 and an outer diameter D2, and it's going to be filled with some sort of material, a dielectric here, that has a permeability and a permittivity. Now we go ahead and go to the next step, which is expressions for capacitance per unit length and for inductance per unit length. We're not going to derive these here. You can find them elsewhere. But essentially this comes out, or the result is 2 pi epsilon over the natural logarithm of D2 over D1 for the capacitance per unit length. Similarly, mu r, the permeability in the dielectric, and the relative permeability over 2 pi times, again, the natural logarithm of D2 over D1. Again, this is for the geometry of the coax cable that we just drew up. Notice in here that we can replace epsilon, the permeability in the medium, with epsilon naught, the permeability in the vacuum, times this term epsilon r, the relative permeability. That gives us 2 pi epsilon naught multiplied by epsilon r divided by natural logarithm D2 over D1. Okay? Now, going back to our expression for Z0, L over C root. This then becomes, we just plug that and that into this equation, mu naught over 2 pi, where we have made the substitution of mu times mu r being equivalent to mu naught. That's really the definition of mu in the medium, or I'm sorry, the relative permeability, mu sub r. So we put mu naught over 2 pi times natural logarithm of D2 over D1. That is divided by the capacitance term, which is 2 pi epsilon naught epsilon r, that's the relative permittivity of the dielectric, divided by, again, this term log of D2 over D1. This entire expression is underneath a radical. Simplifying a little bit, and noting that the logarithm terms flip all the way up from the numerator up to the denominator, since this one is an inverse. So we have log d2 over d1 quantity squared times mu naught over 2 pi. Well, mu naught is actually 4 pi times 10 to the minus 7, to a very good approximation, divided by 2 pi, divided by this term right here, 2 pi epsilon naught times epsilon sub r. This entire term is underneath the radical sign. We immediately cancel the pi's here, we cancel the 2, and we get a 2 up here, and we end up with this expression. Z naught equals to 2 times 10 to the minus 7 divided by 2 pi times epsilon naught, you can find in many books to be 8.85 times 10 to the minus 12 farads per meter. That's the permittivity of the vacuum, times this term epsilon sub r. And of course we have the logarithm times the logarithm of d2 over d1. But note that the logarithm of d2 over d1 is a quantity squared. So since it's multiplied by these constants in the front, we can take it out of the square root. And we end up with the square root of these constants, for sure, times the logarithm of d2 to d1 to the first power. Okay? We can simplify a little bit more and put some values in, but first simplify. Z naught equals to 2 times 10 to the minus 7 divided by 2 pi times 8.85 times 10 to the minus 12. This entire number times 1 over epsilon sub r times the logarithm of d2 over d1. This entire number becomes the square root of 3,596.72 divided by the square root of epsilon sub r times the logarithm of d2 over d1. The reason I'm doing so many steps on this is just so that we don't make any mistakes. Z naught then becomes 59.97 divided by the square root of epsilon sub r log of d2 over d1. This is a familiar expression that you may find. In other places, you might actually find a number like 136 in the numerator here, but that's the cases in which you don't have the natural logarithm, but the logarithm base 10, and they've made that conversion. We prefer to leave it with a natural logarithm. Now, let's put in some numbers. For example, for our RG-8X cable, we go to the Belden data sheets. Belden is the manufacturer of RG-8X that I happen to come across, and we start finding some parameters in there. Like, for example, the diameter, the outer diameter is 0.117 inches of this cable. The inner diameter, the core in other words, is 0.035 inches. And epsilon sub r, we look elsewhere, but we find out that polyethylene foam has an epsilon sub r of 2.1 or thereabouts. We plug that into our equation up here, and we come up with the following. For RG-8X, we have D2 is 0.117 divided by 0.035 equals to this. We take the natural logarithm of that, ln, and then we multiply that times 59.97, which was the result of my previous calculation equals to this, and divide that by epsilon sub r square root, which would be 2.1 square root equals. So we end up with a characteristic impedance for RG-8X of 49.94 ohms, which is pretty close to the listed nominal characteristic of this cable in the manufacturer's data sheets as 50 ohms. So taking a step back, we've gone ahead and worked all the way from a circuit analysis of a transmission line through a derivation of the characteristic impedance. We've actually plugged in some values from the equation that we actually got that relates the outer diameter, inner diameter, and epsilon sub r, or the relative permittivity of the dielectric, in this case polyethylene foam, for the RG-8X cable. We've actually obtained these parameters from the data sheets, and we've actually gotten our characteristic impedance matching what's listed by the manufacturer. So that hopefully gives some insight about what characteristic impedance is and how we can actually apply it in the real world to a real world cable that we all use, and to actually get a parameter that sometimes is arbitrarily thrown around as a characteristic impedance. Now we know where it comes from. Well, this concludes the video. Thank you for your attention.